Hello, hello! Welcome to our next unit here, which is Chapter 4, Exponents and Roots. And so today what we're going to be doing is we're going to be doing Lesson 4.1, which is all on exponents. So I have this lovely little picture here. We'll probably go a little more in depth of it, but talking about how we have a number raised to a certain power, and this power is sometimes called power or sometimes called an exponent. So as we get in, we'll go through our objective here. By the end, you should be able to, it says I can learn to evaluate expressions with exponents. And so this is something we kind of already have talked about when we were talking about order of operations. We talked about how to solve out with some of our exponents as well. But we're going to get into a little bit more tricky situations with exponents within this unit. So here are more of the definitions. So it says a number is an exponential form. The exponent represents how many times the base is being used as a factor. So looking at my diagram, these have 4 to the third or 4 to the power of 3. Your base is 4, so that's what they're talking about with the base. And how many times am I going to use that for? I'm going to use it 3 times. And so that's why I'm going to write out or expand it. Sometimes they talk about expanding it. 4 times 4 times 4. I'm picking the 4 or 3 fours because it says a number product by raising the base to an exponent called a power. So I'm taking it to the power of 3, so that means I have to write out 4 3 times. If I did something instead of, 4 to the power of 5, I would have to write it out 4, 4. I'd have to write 5 4s. And they're all going to multiply by each other. And that would give me whatever 4 to the 5th is. So here's your base. 4 is my base, 5 is my exponent, or we can call it power. And then this is what is called exponential form, this entire part here. The only other thing they have in here says both 27 and 3 to the third represent the same power. So they're saying 3 to the third is the same as 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. So what they're saying is 3 to the third is the same thing as 27, or means the same value. So let's go ahead and take a look at some of our problems. So as we are working with exponents, we need to really make sure that we are reading our directions, because sometimes they're going to ask us to actually evaluate them. Sometimes they're just going to say simplify. But in this case, it says write in exponential form. So really all it's asking me to do is write it with exponents. With exponents. So I'm just going to rewrite this problem. I'm not going to actually figure out what's 5 times 5 times 5 times 5 times 5, so on. I'm just going to rewrite it so that there is a value of that exponent. So I'm noticing that 5 is the thing that's being multiplied repeatedly. So that's actually going to be considered my base. So I could start by writing out 5. And then I got to figure out how many 5s there are. So I'm going to count them off. 1, 2, 3, 4, 5, 6, 7. There was 7, so I'm going to raise it to the power of 7. And that's all I had to do for this, is write it in exponential form. We're going to do the same thing for the other one. Now, if you notice for this one, I've got a parentheses -4. Because all the other ones are parentheses -4, my base is also going to be a parentheses -4. You will see later as to why this is very important to make sure that we are keeping it consistent. So if I notice, it's kind of a little easier to count these, but there are 3 of them. So I've got the parentheses -4 to the power of 3. The last one down here then, though, is I've got 8 and I've got P. So I've got 2 different bases, and that's completely fine. The thing is, though, is you need to know how many of each base. So if I'm looking at here, there's 8 and there's p. Looks to be that there's 4 8s. So I'm going to write 8 to the power of 4. Then I could either put that multiplication, but remember when we just put things right next to each other, that also shows multiplication. So I can write a p, and then I'm going to figure out how many p's there were. 1, 2, 3. 3. There were 8 4s, 3 p's. I cannot combine these 4 and 3 together because they're not the same base. So I have to make sure that the correct number goes with the correct base. So that was just writing them out in exponential form. So rewriting these into a form where there is an exponent in the problem. This time, though, they want me to simplify. Simplify usually means they want the actual answer or the actual solution. I don't know what's going on with my hair. Actual solution. But I do like to write it out just to help me remind myself of what I'm actually doing here. So in this case, in A, you've got 3 to the power of 4, which means you're going to multiply 3, and you're going to write it out 4 times. So 3, 3, 3, 3. And then I'm going to multiply all these together. Now, I'm not going to leave it just like this. I want to actually solve it out. Well, off the bat, I know 3 times 3 is 9. 9 times 3 is 27. And 27 times 3. Let's multiply this out. Oop. Did I do that right? I think it looks like 81. Yep. So here is our solution then, 81. Okay? So it's just showing out that work as well as finding that final solution. This one I've got not a decimal, a fraction. So in this case, I'm going to just rewrite it for a little simpler. And because it's in this parentheses, what it means is that 1 is being squared. I don't know why it's taking a while. And 4 is being squared. So I have to take 1 squared and 4 squared, both the top and the bottom. Well, 1 squared is just 1. 1 times 1. 4 squared is the same as 4 times 4. I want to actually solve out 4 times 4, so it is 1 out of 16. And that would be my solution for this problem. Now, part of it I had mentioned why it's going to be important that we keep some of these in parentheses that start in parentheses. And the reason why is if you have a negative base. So watch how this one, what happens here. Since I have a negative base and I write it out, I need to rewrite it back out or expand it out, sometimes is what we call it, with that base, with those parentheses. It's being squared, so I'm only writing it out twice. Now if I go back and think about my integer rules, a negative times a negative makes a positive. So negative 8 times negative 8 makes a positive 64. And that would be my solution to this problem. Okay? In the case that I have a negative 2 to the third, the way this one is expanded out is I actually write it like this. The negative stays on the outside. And then I worry about just multiplying the 2 3 times. Oops. This is how I would expand this one out. We are taking 2 times 2 times 2, and then we're going to go back and add it in that negative. So 2 times 2 is 4, times 2 is 8. So my final solution is going to be negative 8. So not always are the ones in parentheses going to end up being positive, because in this case, if I were to go, okay, negative 8 times negative 8 times negative 8, we just talked about how a negative times a negative makes a positive, but if I have a positive times a negative, my answer is going to end up being negative. Any case that you have no parentheses but the negative on the out like this, it means your solution will always be negative. okay? So parentheses, if they have parentheses and then the exponent on the outside, depends on what the exponent is. If there's no parentheses and there's an exponent, a negative in the base, it's always going to be negative. That would be a really awesome thing to write down in your notes so you can remember. We've only got about 2 more to go through. So another thing you might see is evaluate. So this is something we've been working on since chapter 1, which is evaluating expressions where I'm given different variables and I need to substitute in or plug in those values. So they want me to evaluate this equation right here, which looks to be x minus y times z times y to the z. They tell me that x is 20, y is 4, and z is 2. So what I'm going to do is I'm going to start by plugging things in. Now it says x minus y and then z times y to the z. So x, instead of writing x, we're going to plug in 20. So I'm going to write 20 minus, then they say y is 4, so I'm going to plug in 4 for y. Then I'm going to add my parentheses. They say z is 2. I'm going to multiply, and then we have y to the z. Y is 4, z is 2. Thinking about my PEMDAS. I want to do anything in the parentheses first. In the parentheses then, I also have a multiplication and an exponent. So if I think back into parentheses, or my PEMDAS, exponents are what we solve out first. So I'm going to have 20 minus 4, 2 times, and then 4 times 4, which is 16. From there, then I can multiply in my parentheses. So 20 minus 4 times 32. Once I have that, the next thing is this multiplication of 4 times 32. So I still have this 20 minus, when I do 4 times 32, I get 128. When I subtract these, 20 minus 128 is going to actually give me negative 108. And that's my final solution. So using your order of operations, using substitution, plugging those things in. Okay, so you will have a couple questions like this. Take it one step at a time. So start by rewriting it and plugging things in. Then worry about your PEMDAS. I think we have one more problem. This one, I believe, is another kind of substitution-ish problem. It says a number of diagonals on an n-sided figure. So if you ever played Dungeons and Dragons and you get all the different types of sided dice. So what they're talking about is the number of diagonals of an n-sided figure. So maybe one of those dice is this equation right here, 1/2 times n squared minus 3n. Use the expression to find the number of diagonals on a 6-sided figure. So it's n-sided. So if I'm going to say it's 6-sided, that's showing me that I'm going to have n equals 6. So what I'm going to do is I'm going to plug this in this equation. So here's the original equation. I'm going to plug in 6 for n. So now I'm going to have 1/2 6 squared minus 3 times 6. Order of operations says my parentheses. And I know I put in a parentheses here to show multiplication. But there's no operation to do in here. So we're actually going to do the exponent first. So 6 squared is 36. And actually in the same step, I could do this 3 times 6 minus 18. I get 1/2 times, which I think that's also 18. Once I have that, I'm taking 1/2 times 18, which is a lot like saying 18 divided by 2, which actually gives me 9. So there are 9 diagonals in a 6-sided figure. So we will continue working on these problems here in class, and so I will see you guys then.